All right, so tangent line. When I say tangent line, what comes to mind? Touches.
The graph.
Touches the graph.
Exactly one.
Thank you, Jonathan. All right, so it touches the graph at exactly 1 point. So we talked about how, some graphs will straighten out, and when they do, what's that called? When you zoom in repeatedly until the graph straightens out, we say that that has blank, blank. Nope. No. Mm-mm.
It's in
Blank, blank. Nope.
Guys, get it
It's a-
together.
Nope.
It's called a
Direct substitute.
Nope.
no.
Any two combinations of words. Let's just keep going. We'll get it.
Apple pie.
No. Not apple pie and not stop sign. So it straightens out, and so line is a good place to be with that. It has something to do with a line. We say that the graph has from the first day of school. Told you to remember it. I know, Miranda, you're off the hook. Mm-mm.
Rate of change among curves.
If the graph can straighten out, it has
Tangent properties.
not tangent properties.
Limits, composition. No.
No.
Was this the notes from that night?
I'm not telling y'all.
Can't find my notes.
I'm not telling y'all. Y'all don't know. I'm asking you on a pop quiz.
Where did it go?
Yeah, Miranda.
It has a tangent line.
Nope.
I have no idea what I took those notes on.
All right. Well, that's okay. That's okay.
Oh, wait.
Y'all will figure it out. Somebody will figure it out sometime. Nope. All right. So the idea here is that we are going to use the slope of the tangent line to think about what the rate of change would be along a curve. So since a curve isn't constant, as I move along that curve, I'm going to have different slopes depending on where my tangent line is. So until we really learn enough calculus to be able to do this, we're going to begin with what we call an approximation of the tangent line, and we're going to use a line that passes through our curve at 2 points. So what's that called? Love it. Good. Secant line. So we're going to use a secant line approximation to approximate the rate of change on our graph at any particular point. So we're going to have, let's think about this bottom point here as x comma f of x. And then this point is going to be to the right of our original point, and let's go ahead and say that it's an increment of h. Okay, so I'll zoom that in a little bit more. So let's just think about I'm a distance of h over till I get to my other point. So how would I write the ordered pair? If I move h to the left, to the right, how could I write an ordered pair for this point? Any ideas?
X plus h.
Good. X plus h, comma. Good. F of x plus h, because then that notation would just signal to you that you would take the x value wherever you are. Once you shift over h, units or increments to the right, you'd plug in that value. Oh, I guess we technically need to close our parentheses here, so double parentheses. And so let's make a note when you go back and look at this. This is an approximation. So this is the approximation.
How will we know what h is? Like, will it give that to?
Yes. But we're actually going to bring in another idea that we know. All right, so derivative. I want you to just think that a derivative, so if we say the derivative of f of x, I can write that as f prime of x. So we're going to read that as f prime. And a derivative is, in very simple terms, I want you to think that is the slope of tangent line. Okay, so the slope of the tangent line gives you the derivative. So how we're going to start until we learn our derivative rules, we're going to solve for the rate of change at a particular point on a curve by using, like if you have to think about writing the slope of the secant line here, and maybe label that if you don't think you'll remember. So we're using the slope of the secant line. If you had to write a slope calculation here, think about slope formula. Slope formula, y2 minus y1 over x2 minus x1. If I do that, I'm going to have, let's just think this is our y2, so I'm going to have x2, y2, x1, y1, and so then to get the slope using the secant line, I'm going to set up f of x plus h minus f of x all over, and then if I have x2 minus x1, what's that going to simplify to? If I take
H.
just h. Okay, so I'm not going to write it. I'm not going to have the x's there. I'm just going to go straight with the h. But that's what we're doing. We're saying rate of change. So we're saying y2 minus y1 over x2 minus x1, but we're not going to put the x's because they're going to take each other out.
This is that one formula.
So what is this called? Do you guys, anybody remember?
Point slope form.
Okay. This is the,
Point.
no, not point slope. I don't ever want you to think this is point slope. This is the difference quotient. It's okay.
I recognize it though.
Good. That's all I need at this point. I need you to recognize it.
I have the answer to your question from earlier.
Do you?
Was it limits analytically?
No.
Was it intermediate form?
No, it's not even on that note sheet if you're just going to keep reading words off of that. All right. Limit. If you take the limit as h approaches 0, I want you to think about why we would do this. So a second ago, Jacob, or we asked how we know what h is. The idea here is that if you want to get a good approximation of the tangent line, you want to be really, really close to that point. So remember on the first day, not you, Miranda, I'm sorry, but on the first day when you zoomed in and it straightened out and we went 1 pixel over, so we were really, really close to our original point. That's kind of what we're trying to do here. We're thinking, okay, I want h to be really small, because the bigger h is, the worse of an approximation I'm getting. So the more I guess close to 0, which is why we're going to put this through the limiting process, the closer I get to 0, the better my secant line is going to mirror my tangent line. So in order to kind of use some calculus in this, we're going to put it through the limit process. One more thing to just kind of get floating around in your heads for future reference that we'll refer back to many times this year, so it's okay if you don't know it right off the bat here. But the more we kind of, just talk it through, hopefully it'll stay with you. When you put the limit as h approaches 0 in front of the difference quotient, this is referred to as the definition of the derivative. So definition of derivative, you're using a secant line approximation with a value of h that approaches 0 so that you can essentially determine what the rate of change would be at exactly 1 point. So we want to get really, really close in there to that point. We want h to be as close to 0 as we can possibly get it. But if we plug in a 0, then that gives us indeterminate. So we can't just plug in a 0 here, because we're going to get a 0 in the denominator. That's going to drop out, and we get 0 over 0. That's not any good. So I can't direct substitute this, so I'm going to have to put it through our fabulous limit process. So any questions on the concept yet of what we're doing? So conceptually, we're using a secant line and using a slope calculation for the secant line to approximate the rate of change at an exact instant, which is what we call our tangent line approximation. And the rate of change at an instant, so at just exactly 1 point along a curve, is what we call the derivative. So when you get the derivative, you're finding the slope at a particular point along a curve. And we're going to do that using our difference quotient, but our notation for that would be f prime of x. So the derivative of f of x, we write it as f prime, read as f prime, and if you have limited calculus skills, you can calculate the derivative, but this is kind of like the long way. This is the longer way to do it. So sometimes we get stuck having to do it this way, but we'll learn several functions that we can work with and learn patterns and rules that'll make this a little bit more user-friendly. So we're not always having to crank this out. But we need to start with that so that we can build. So this is kind of our foundational piece.
Okay. So for the secant line, so like the secant line is really close to the tangent line, like approximately?
Yes.
So that's why we
want an h close to 0. Because if you pick an h value that's big, now I couldn't get too close here because I wouldn't be able to just with the naked eye discern it. So I made h look a little bit bigger than you would want. What we're picturing is if I could zoom in until it straightens out and then go over 1 pixel, I'm trying to just get to a place where h is practically 0, where I'm not really moving over much at all. Because if I pick a really small value, then my secant line should essentially be pretty much, as far as an approximation, should be a pretty good approximation of the tangent line. But if I pick a big value of h, like if I pick a point here and a point over there, or a point here, and so if like this was my original point and I pick a point up here, the farther I get away from that point, the worse this line is going to get as far as off of the tangent line. The slopes won't be close. Yes?
So the point of what we're trying to do is find like the slope
Mm-hmm.
at a certain point.
Yeah, I want the slope at that point, but I'm limited right now with my abilities. Okay? So I'm going to use that to get the slope of that. All right. So we need to get comfortable with things like find f prime of t if f of t Okay, so you know how a lot of times you feel like you do an easy one and then like you work the problems and then they're harder. So I picked like one of the harder ones. So I think that some of them, when you get to the assignment, like we're going to do a hard one together, and so the first couple in the assignment aren't going to be as hard as this. This is going to be a nastier algebra one, but I think it brings up some things we haven't done in a while. So if you get lost anywhere in this, please let me know. So we want to find the derivative of that. So if I ask you for the derivative, right now we're stuck with using the definition of the derivative, which is taking the limit as h approaches 0 of the difference quotient. So for f prime of t, that's going to be the limit as h approaches 0. Yes, you have to keep writing that, I'm sorry. And so instead of f of x, we have f of t. So the first time you're going to plug in t plus h into your function. So instead of having 2 over t, and if you want maybe like brackets instead of parentheses here, just because it's going to be kind of ugly. Okay, so that's what the first step of the difference quotient should feel like. You're taking whatever your variable is in your function, no matter how many of them you have, and you're going to replace them all with that variable plus h. So if it was x, you'd replace it with x plus h, but it's t, so we're replacing it with t plus h. And then we'll always have subtraction because this is a slope calculation. And then we'll have our function the way it was originally written, and we'll have it all over h. And we're taking the limit as h approaches 0. That's what's going to make this the derivative. All right. Any questions with the way it's set up? All right. So can I combine those fractions in the numerator? No. Why can't I? Great. So I don't have a common denominator. So how am I going to get a common denominator?
By adding h to the top and bottom.
Well, you can't just like you can't multiply by plus h, right?
Yeah.
That's kind of the issue.
Denominators on the top.
I'm going to have to multiply each fraction by each other's denominators.
Oh, yeah.
Boo. All right. So I'm going to have to come through here and think, all right, this guy is going to need the t plus h, but then this one's just going to need a t. So then my common denominator is going to become t and then like parentheses t plus h. So this little guy is going to get hit with a times t over t, because remember, you want to feel like you're multiplying by 1 here. And then minus and 2 over t. This time we're going to multiply by t plus h. This is all divided by h. I will have lazy students that are like, I'm just going to start writing it at the end. A lot of times you will forget. Okay, so please just keep it going here. You don't have to do this all the time. I know today it's going to feel like, yeah, I do. But throughout the year, you're not going to have to do it all the time. Please keep writing that over h. The limit as h approaches 0. All right, so we're going to go ahead and multiply this out. So I'm going to get 2t. And then I'm just going to go ahead and combine. We can do it. I'm going to go ahead and put them all over their denominator right now. So I have 2 times t, and then minus. You're going to need to distribute that t. To distribute that t through. So it's like I'm going to have minus 2t. And then I'm still taking, you can go ahead with the negative 2 or minus 2, and then times that h. So you'll be subtracting there also. Good. Now this is still all over. All right, so I have room. I'm going to keep working down, actually. Limit as h approaches 0. So at this point, we've got negative 2h over t plus h. So when we get that indeterminate form, it means that there's a common factor. Now, right now, I've got a fraction divided by h. I could go ahead and look at it almost like I'm putting h over 1. And then that way I don't have a fraction divided by a fraction, but I have a fraction times, good, the reciprocal, 1 over h. This is the reason I'm getting the indeterminate form, that 0 over 0. So my h's need to go away. So just think about like normal dividing out technique. What do we do with the limit stuff after you get that factor to cancel? Like if you got x plus 2 in the numerator and x plus 2 in the denominator, and you divide that out, what would we do after that as our next step to finish the problem? Now we're going to have a bad test on Wednesday. We would direct substitute. Okay, so once you get the common factor to divide out, now you want to direct substitute. Wednesday. Okay, so when I direct substitute, meaning I'm going to plug in a 0 only for the h. Okay, so when I plug in a 0 for the h, good.
My t's look like my pluses.
And this is going to be the equation of so this is the derivative, and remember, derivative is like the slope formula. So now, if I ask you for a rate of change for this function, say, hey, what's the slope at a point? Even though the function is a curve, I'm going to be able to plug in an x value and get the rate of change at that particular point. So for right now, this is the process that I need us to be able to go through. Questions on that? I know it's an algebra intensive one.
Wasn't too bad.
Okay. Good. This is continuing with the same, I just don't have room. So I'm going to ask you to find the slope of the graph of f of t at the point 1 comma 2. If you want the slope of the graph, what we want is the derivative. And we want the derivative when x, or t in this case, is 1. So this is what you're looking for. F prime at 1 means what is the slope? What is the slope of the tangent line? What is the rate of change at the ordered pair 1 comma 2? So we use the derivative formula we just calculated. And so remember that formula is f prime is equal to, or f prime of t rather, is equal to negative 2 over t squared. So I'm going to take negative 2 over 1 squared. And this is going to give us negative 2. And we're going to write that like this. So read as slope of the tangent line.
Wow.
Okay? Slope of the tangent line.
Oh. Wait.
Go ahead and ask. I'm just going to write this out because that's our last thing on the agenda. What's up, Jacob?
No, I'm fine.
Okay.
So you just found the slope by plugging that in?
Mm-hmm. To your derivative.
So the M stands for slope.
Yep, M stands for slope, just going all the way back to like algebra 1. As long as it's the derivative, it will always be giving you the slope of the tangent line at that point. So that's what derivatives will do for us. They will give us the slope of the tangent line at any point. So if you want to pick a different point, that's why we like to get the derivative, so that instead of having to solve for the slope by hand, the way we did on the first day of school by doing slope calculations at a bunch of different points, we just create a function that can give us that slope at any point a lot faster. Now this is a great AP question that should be a gimme question. They love to say, create an equation for the tangent line at a point. And Jacob, you actually brought up point slope earlier. And that's the formula we want. It was just out of context. So point slope, that formula,
Y or AX or BY. No.
that's the standard form. That's the standard form.
Must be covered up.
Oh, yeah. How do I think that makes sense?
I don't know, but that's okay. All right.
I think I meant slope formula. I don't know why I said points.
I don't know, you just felt like it. All right, so point slope, that's your point slope formula. To create an equation for the tangent line at that point, here's your x and y. So that's what you should be using for x1, y1. What's the slope of the tangent line? At that point, right? We just found at this exact point, we said the slope of the tangent line was negative 2 because we used our derivative. So you plug the point into the derivative, you get your slope, you use the point it passes through in point slope form, and you don't need to solve it.
That's good.
For y, that is your answer.
Oh, the
That gives
equation.
you the equation of the tangent line for that point for this function.
Well,
That's pretty sweet. It all just comes together.
It comes, it does. Getting the derivative is the key here.
so many connections to like what we